Good morning, everyone. Okay, before you put your question up, of course, by now, all of you know that the exam is this coming Monday, so in a few days. It's comprehensive, your review is out there, and the exam will open at 7:30 in the morning on Zoom. So you use the same link that we always use for the class, and it closes at 10:30. Okay, so it opens at 7:30, closes at 10:30. All the info are on Brightspace. All right, so questions, Chris? So we're gonna finish the hyperbola and then we will start doing some review today and tomorrow. So yesterday we established the equation of mainly we did not establish it. I gave you the equation and we analyzed it. So the basic equation is equal to 1. This is where it's centered at the origin, or y squared over b squared minus x squared over a squared equal to 1. That was the equation. The hyperbola is characterized by its asymptote, which given by that in both cases is the same formula. What's under b, under y. In this case, the opening is, once we build the asymptote, the opening is left, right, and the intercept are a minus a. And then in this scenario, these are the asymptotes, same thing, but the opening is up and down. This is my b, and this is minus b. So the b is from here. And then I finish by mentioning that we can have a shifted one, and the shifted one is exactly always the shifted, like the ellipse. So instead of x, we'll have x minus h. And the big minus in here, or y minus k squared over b squared minus equal to 1, okay? And what I wanted to say, and this is called the standard form of the hyperbola. That's what we call standard form. So with this in mind, we're going to look at the problem that your classmate asked us for, and then we finalize, all right? So I start by looking at number 21. Number 21. Okay, so we have the following: y squared minus x squared equal to 1. Okay, now in a hyperbola, we can have a equal to b. I mean, we can have that also in the ellipse, which make the ellipse into a circle. But here we can have a is equal to b. And this is the minus is right there. So it's a hyperbola. And this hyperbola, because the minus in front of the x squared, not the y squared, is going to be opened up and down. So let us figure out everything they want. So first, we're going to find the vertices. The vertices basically is the intercept in this scenario. So the vertices are going to be, so here we have the b square is 1. So my b is 1. And the a square is 1. It means my a is 1. So this is because the vertex is up and down. The vertices are 0 plus or minus 1. Now we need the foci. For the hyperbola, the formula for the foci is easy, is a squared plus b squared, which is equal to in this case. So the foci are 0 plus or minus the square root of 2. The asymptote are y equal plus or minus b over ax. My b is equal to my x, so this is plus or minus x. So we have two asymptotes. y equal x, and y equal minus x. Right? So that's, and now we're going to definitely to sketch the graph. Usually we start by sketching the asymptote because they give us an idea what to do when. So this is my asymptote right here, and this is my asymptote. This is nothing more than the line y equal to x and y equal minus x. And now we have to draw the vertices. So actually, if this is 1 here, because this is the line y equal to x, so this is my 1 here, and this is 1, this is my minus 1. So when x is large, the asymptote is right here. So that's how the behavior is. And this function will go this way. And then exactly the same. It's total symmetry, even though in my graph it doesn't show symmetry, it should show a total symmetry in the graph. This piece symmetric to that, this is symmetric to this, and this is symmetric to that. Okay. So that's my basic hyperbola in this case. Now we look up number 23. 23 is those completing the square problem. Okay. So we have 2 y squared minus 3x squared minus 4y plus 12x plus 8 equal to 0. Okay, so it looks a mess, of course, and the idea is complete the square so it would look totally like a standard hyperbola. All right, that's really what we're going to be doing. So let's start doing this. Okay. So here we realize that the minus is in front of the x squared. So I'm going to first rearrange. So I will have the y's together. And then I'll put the x's together. And my constant term, I move it to the other side. Okay. And now we have to start computing the square. Because the coefficient of y squared is not 1, it's 2, I first start by factoring it out. I'm going to factor it out. So I can compute the square inside because the algorithm only works when the coefficient of y squared is 1. Here, I need to factor out the minus 3. So I have to be very careful. Factor out the minus 3, I'm left with x squared minus 4x. This is equal to minus 8. Okay. Now I'm computing my square. So it's going to give
I have a question real quick.
Yes, yes, please.
Will the problems always be like so where you can take it out easily? Like the
I mean, technically
like
they shouldn't. They shouldn't. But the problem that you will be given, they will.
Okay.
But there is no reason for that. Absolutely no reason for it.
All right.
Okay. So y squared minus 2y, I have to add a 1 here, but I have to take it away as well. Minus 3 x squared minus 4x. To complete the square, I need to add the 4. I have to take it away, otherwise I will be changing everything. And now we are almost there. So this 2 times. This will become y minus 1 squared minus 1 minus 3. This is x minus 2 squared minus 4 equal minus 8. Finally, I distribute. You have to be very careful. So we'll have 2 y minus 1 squared minus 2 minus 3 x minus 2 squared minus minus plus 3 times 4, that's a 12 equal to minus 8. So finally, I mean, almost there. We have to get it into the standard format and then we can analyze everything. Equal. Now minus 2 plus 12, that's give me a 10. And then I'm going to bring the 10 from the other side. It's going to give me minus 18, right? Okay. Now to get it into the standard form, I need to divide by minus 18 across, and that's what give me if you divide this by minus 18, this by minus 18, and this by minus 18. So I'm going to get my 1 here. Minus minus, that's a plus. X minus 2 squared over 6. And this I will have minus over 9. Okay. Now the minus is in front of the y. I'm going to rewrite them. So in the more standard form, this will become that. So that's the standard form. And now we're going to take this one and we're going to find everything they want us to do. Question before we finalize it. Okay, so this is my hyperbola now. So my hyperbola is x minus 2 squared over 9 minus y minus 1 squared over 6 equal to 1. Okay, so that's really what I have. So this is the so this is basically what is this?
Wasn't it the other way around?
No, because when we divided by minus 18, this plus turned into a negative.
But it says right there x minus 2 over 6.
Oh, I thought what you meant is the y first and the x.
Oh, no, sorry about that. I should have been more clear.
Yeah, you're right. Very good. So now this is basically the following hyperbola. This is basically this hyperbola, exactly this one, being shifted. That's what it is. So that the center is 2 and 1. So as this one is going to be shifted, basically, the center is 2, it's going to be shifted. It means horizontally 2 unit and up by 1. Shifted up by 2, no, up by 1, right to the right by 2. Okay, so it's basically this hyperbola that you are shifting. All right, so what's the center here? The center is going to be 2, and it's going to be 1. Okay, and this is going to be up and down. I meant since x here, so it's going to be left and right. So let us start building it slowly. The only thing we have to be careful is the asymptote. That's the only thing we have to be careful with. So this is 2, and this is 1. Okay, so, okay. Now, for the vertices, let's note here is that my a square is equal to 6. A is the square root of 6. It means that starting here, we're going to go square root of 6 unit, so which is a little bit over 2. That's my A, so that's the intercept, and right here. So this is the square root of 6. And this is my square root of 6. So the vertices are going to be, they're on this line right here. So it's going to be 2, add square root of 6, and a 1, 2 minus the square root of 6, and 1. Okay. So this is going to look like that. Now the foci, okay, c squared is 9 plus 6, which is 15, means that the foci will be inside here, to be somewhere here and here. So the foci are going to be, so this is my C. That's the square root of 15. And the foci are going to be 2 plus minus, you can write them in one writing, 2 plus or minus square root of 15 and 1. And finally, the asymptote. Okay, what are the asymptote? Anybody figure them out? Remember, this time, that's the center. So the asymptote in the scenario will not go through the origin necessarily. So the asymptote are going to be here. So the point on the asymptote is going to be 2, 1, because everything is going to be shifted. everything is going to be shifted. So basically, the way I look at this one is like the standard one. So it's this one, which everything is being shifted. All right. So what's going to be the asymptote? What's going to be the slope of the asymptote? We're going to have, of course, two asymptotes. What's going to be the slope of this one? It's the same slope of the one that's not being shifted. Because when you shift, the slopes remain parallel to each other. So the slope is going to be, of course, we have 2 plus or minus the b, which is the 3 over a, the square root of 6. That's going to be the slope. But those asymptotes go through the point 2, 1. So the point is 2, 1. So the slope and the point. So the equation are, you have two equations. The first one is y minus 1 equal the positive x minus 2. And the second is y minus 1 is the negative x minus 2. Okay, so that's the only thing we have to be careful with is this asymptote. The slope is the same. It's plus or minus b over a, but the point is changing. It's not going through the origin anymore. It's going through the point 2, 1. And that's how we get the asymptote.
So those equations you just wrote off in the bracket, those are just showing that you're adding 1 to the y and adding 2 to the x for the center?
I'm trying to, this one you mean?
Yeah, can you just
yes, because we're shifting the lines as well.
Okay, so those are those the asymptote equations?
Those are the asymptote.
Okay.
Those are the asymptote, yeah. So the graph is going to look as usual, like those are the asymptote. Did you understand how I got them though?
Yeah, I understand it all up to that point, yeah.
Yeah, because the slope are the same slope as the one that's not shifted, the original slope. And this is the b is 3. The b is the 3. And the a is the square root of 6. So, and you remember the previous one, the equation was plus or minus b over a x. So this is the slope. Plus and the minus slope. That's the slope for the one non-shifted. But now when you shift them, what will happen? The slope isn't remain the same because those are parallel to each other. So the slope is remaining the same, but it's the point that's being changed. They don't go through the origin anymore. They have to go through this point. So that will become the point on the asymptote. So that's the slope of the asymptote, and that's the point. And then here I actually just use the point slope form of a line to get me the equation. All right. Anybody else? So that's the only difference here is that you have to be careful with the slope because it's not going to go through the origin anymore. It has to go through the center of the hyperbola. Right. So let's finalize with number 43. What is number 43 about? We have to write the equation of a hyperbola. They gave us the foci and they give us the vertices. So foci and the vertices. And the foci are 0 plus or minus 3. And the vertices 0 plus or minus 1. Okay, so a little bit kind of a picture so we know how we work with that. So the foci are 0 plus or minus 3. So right here and right here. And the other one is 1 and minus 1. So it's going to look something like that. Okay, they didn't give us the asymptote because we don't know them yet. So Step number 1, the form. The center is at the origin in this scenario. So the equation, and since it's going up and down, so it's y squared minus x squared over a squared equal to 1. Okay, and now we have to find everything, b and a. This is the b right there in my problem, is the intercept. So we know that b is equal to 1. Now we need to find the a. For the hyperbola, foci is a squared plus b squared. So now we have everything. We know that c squared is 9. This is a squared plus 1. It means a squared equal to 8. And this hyperbola will have for equation y squared over 1 minus x squared over 8, over 8 equal to 1. Any other questions before we proceed? All right, so these are the conic section that, as I said, you will be using them absolutely later on in your later courses. So it's important to know the form of each one of them, how they look like. I mean, the equation and how to recognize it. I mean, the minute you see, starting now, the minute you see an equation like this, whatever plus y squared over 4 equal to 1, you have to see immediately that this is an ellipse. I mean, you have to really see that this is an ellipse, okay? Sometimes we study parametric equation a little bit in this course. There is a way to get a parametrization that give us an ellipse. So before I mention that, first I want to mention one thing about the foci for the hyperbola. You know, ellipse, I told you the property of the foci. For the ellipse, the property of the foci is that if you put a source of sound in one of the foci, it reflects all the way to the other foci. So that's really had this nice property. Hyperbolas also, that's why the foci are important, have the following property as well. And it's used for headlight and mirrors and those kind of things. They have the following property. Suppose the foci is here and that's another foci. And let us say this is a mirror. Okay. And the property is that if you take a source of light and you direct it toward the foci, so directed toward one of the foci, what will happen is that when it hit the mirror, the light will reflect back to the second one. That will be its direction. And those ideas are used in building mirrors and stuff like that. So that's really the important property of the foci. You take a source of light, you direct it toward one of the foci. If you have a mirror here, the light is going to reflect, but in which direction? It will reflect in the direction of the other foci. That's the direction that it will take. So that's the property of the foci that they are matters. Now, another comments about parametrization. So suppose I tell you the following. So back to parametric curve. Okay. Suppose I tell you, let's consider the curve given by the following parametrization. X equal, let us say 2 plus 3 cosine t, and y equal 5 plus 2 sine t. Okay. Now I give you the same type of problems where I put 3 here and I put 3 here. And we got a circle. That's the one you had on your previous quiz. Now if I change the multiplier, the thing I'm multiplying sine and cosine, what do I get when I graph this? If I imagine you have an object moving with time, and for every moment in time, that's its x and y coordinate. So it's going to move. And the question is, what shape you're going to get? Okay. All right, watch here. I'm not changing. Watch here what's going to happen. The first, as we did before, will give me x minus 2 over 3 equal to cosine. This one would give me y minus 5 over 2 is equal to sine. So now when I square both, this is equal to 1. So it means that if I take x minus 2 over 3 square plus y minus 5 over 2 square, we get 1. Now, if I do a little bit of algebra, I get x minus 2 square over 9 plus y minus 5 square over 4 equal to 1. And I get an ellipse. If I totally eliminate the t between those two, I will get an ellipse. And this is what we call the parametrization of the ellipse. So this is an ellipse centered at 2, 0, at 2, 5, somewhere in here. And then we know everything about it. We're going to move 3 units from here, and then we go 2 units up, and 3 units, and then 2 units up. So this is really the ellipse. Okay. At t equal to 0, I will be right here, and we move on in the clockwise direction. Okay, so that's a good way of parameterizing an ellipse. At this stage, I am personally done. I would like to start a review with you. Do you have anything that you would like me to review specifically before I take off? I decide.
Could you
Part
do
of the course these are uncomfortable with?
Could you do just one of the shell method problems?
Cylindrical shell, you mean?
Yeah, the
Okay.
finding area under, or I'm sorry, the 3D shapes where it's rotated around an axis, but using the shell method, yeah.
Okay, so cylindrical shell. And you want a rotation around x-axis, right?
Yeah, that works.
Okay, whatever you guys want. So let's make up a problem. Let's make something up. So we'll take a simple curve. So the curve itself will not give us an issue. Let's consider the curve, I don't know, y equal x square for x between 0 and 3, for example. Revolve around the x-axis and use shell method. So the problem is very clear. Use the shells method. So we're not going to use the washers method. All right, so always graphing. That's the starting point for any of those. So I'm going to start here. This is y equal x square between 0 and 3. This is the region. And we want it around the x-axis. So this is the x-axis right here. And we want to revolve that, okay? Now, the shell method, it means we take slices. So if this is 3, right here has to be a 9. The shell method means that you have to take slices parallel to the axis of rotation. So if I'm going to take those slices right there, it means y is my variable. It means in my mind, that's the interval I am splitting into pieces and rotating every piece. So we have to be very careful. Y is the variable. Y is the variable. Okay, and I rotate each one. So this is my Y. I'm going to rotate this, and that's what I'm going to get my shell. I didn't rotate it very well. All right, so this is my shell. My shell, the volume of a typical shell is 2 pi times the radius times the height times the thickness. Okay, and as you know, we have to figure out every aspect here. So we're going to know what's the radius of a shell, radius of typical shell, what's the height of a typical shell, and what's the thickness. Okay. All right, let's see the easiest one. What's the thickness of the shell?
Delta y.
That's the delta y. Y is my variable. That's the little thickness. Now, what's the radius? When you're rotating it, the radius is from here to here. Remember, y is my variable. Everything has to be expressed in terms of y. So what's the radius in my picture? So that's my radius. It's equal to what? Look at the picture. Y is your variable.
Y.
How much? That's the y. Or yi. I mean, I remember
Yeah.
we used yi in this class. So the radius is going to be the yi. Now, what's the height? The height is from here to here. What is the height?
Won't that be 3 minus x squared?
No.
Or yeah, don't we have to change x squared to
Right. We have to change everything in terms
square
of
root
y.
of y?
Right. Everything has to be expressed in terms of y because y is my variable. Right. Everything. So we know that y is equal to x squared. It means x is the square root of y. We have to change everything in terms of y. And now let us remember that we're finding the horizontal distance between those 2 points. Basically, that's what we're finding, the horizontal distance. So it's the value to the right minus the value to the left. So this is a 3, and this is supposed to be, this is the square root of yi. So if this is yi, this is the point on the curve. It means I want the x of it, is the square root of yi. So this is right here is the right value minus the left value. Okay, so it's going to be 3 minus the square root of y, the right minus the left. Okay, because we wanted rotation around the x-axis, so my slice has to be parallel to the x-axis and to everything in terms of y. So now volume of a typical shell. So this is every aspect. So volume of typical shell is almost equal to pi times the radius times the height times the thickness. Okay. Now the total volume, so volume of the solid when it's rotated is the sum of those terms, which is our Riemann sum. Okay. So now the volume is what happened to those sum when n becomes very large. And this is where the Riemann sum get into the picture. So it's 2 pi y, 3 minus the square root of y dy. And to find the limit, we ask ourselves to cover the region, which interval we have to divide. This is my region right here. I have to divide the interval from 0 to 9 by little pieces to be able to cover the region. So that will be the integral from 0 to 9. Okay. You guys remember it now a little bit?
You got the 9 because you had to solve for,
yes. What's my variable? What's my variable in this problem?
the y.
The y. Y vary from where to where? If this is 3 right here, this point is what? If x is 3, this has to be 9. This point right there.
So you just set the square root of y to 3 to equal 3, and then you just solve.
You don't have to, because the original curve is y equal x squared. So if this is 3, right?
Yeah.
The y is 9.
Oh.
From the original expression. I didn't really need to do anything at this stage.
All right.
Okay?
Yeah. All right. Sorry about that.
No problem. No problem, guys. Now you can do anything. On Monday, you're on your own. Any other question from Michelle? Go ahead.
What were the types of finding the antiderivative? It was before the
Chris, you have to be precise in your question.
yeah, someone else can answer. Let me find this out real quick.
Okay, all right. Okay.
I have a question too.
Go ahead.
How do you know that y is going to be the variable in that situation, or that x works just as well?
How do I know which one is in the variable?
Yeah.
You ask yourself, in this case, we have to take horizontal, horizontal slices, right?
Yeah.
Okay. If you take horizontal slices, it means which interval are you dividing? The interval on the y-axis or the x-axis?
Could you use the x-axis one though, and then do up and down ones, or does that not work?
You can, but you will not get a shell. You get something else.
Oh, okay.
All right. Okay. Let us say, so to know what's the variable, you ask yourself which interval I am dividing to cover my region. If you're taking horizontal slices, it means you're dividing the interval along the y-axis. It means this little thing is the delta y. Y is my variable. Now, if I take this same problem, so I did cylindrical shell because you guys asked for that. If I take this exact same problem and I tell you find the volume without really telling you which method you use, you could have used the disk method. So let us remember that. So the same region, because I don't want the region to be problematic. Again, revolve around the x-axis. I'm not changing, but this time I'm not going to use the shell method. I'm just going to use the disk method because I think it's easier in this problem. So let's remember how to do the disk method. It means we take slices perpendicular to the axis of rotation. In the cylindrical shell, we take them parallel. So let's see how the picture will change in this scenario. And then this is my piece. Okay, that's my region. And this is my axis of rotation. And I'm going to take slices which are perpendicular to the axis of rotation. It means this is 0 and this is 3. I mean, these are my slices, like that. Okay. In this case, immediately x is my variable, because to cover this region with slices, okay, I have to divide the interval on the x-axis. But now the whole picture changed. If I take this piece and rotate it, I'm not getting shells anymore. I'm getting nothing more than a simple disk. Okay, so in this case, what's the volume of a typical disk?
Pi r squared times the height.
Right. It's pi times the radius square times the height. Okay, and then we have to figure out every aspect of it. So what is the radius in this case of the disk? And what's the height? So this is basically my xi. Okay, the radius. That's the radius of my disk. And the height is this piece right there. Okay, so what's the radius of my disk now? This is xi. The radius is nothing more than the value of the function. So it's xi squared. The height is the little bit, is the delta x in this scenario. So the volume will become pi times xi squared times the delta x. X is my variable because the idea is that you cover this with those with those rectangle. And then you actually rotate each one of them. And by rotating each one of them, you're going to basically get the whole the whole solid that we're rotating. So we're approximating the whole solid by the sum of the volume of those little disks. That's really the picture we have in our mind. So we evaluate the volume of each one of them, and then we're going to add. X is my variable because, again, you're dividing the interval on the x-axis into pieces. So now the total volume is going to be the integral from 0, sorry, I did a mistake here, 0 to 3 of pi, this is the dx, x squared dx, which is x4 dx, and you finalize. Okay, so in the cylindrical shell method, we took slices parallel to the axis of rotation. In the disk and washer, we take slices perpendicular to the axis of rotation. Now,
All right, thank you.
Is that making any sense?
Yep.
Okay. All right. Any other questions about those before I move on myself? I mean, before I move on to the review. All right. So what I had in mind for the review is the other part, you know, that usually shouldn't forget and mess up with is work. So if I have time, I would like to do the first problem in work, and then I will set up the second one. Okay, so this the goal of this to remind you work of pumping water. For the spring, it's just a formula. Make sure you know it, because when I give you a spring problem, it means I'm giving you an easy problem. So make sure you go over the spring. And if you have difficulties, we work on them tomorrow. So this is a typical work problem where we're pumping water. So I will read it and I will remind you how do we proceed with those type of problems. So we have a cylindrical tank. So I'm starting with an easy one and then we do a harder one today or tomorrow. A cylindrical tank of radius 4 feet and height 10 is filled with water to a height of 8 feet. So we have a cylinder. That's the cylinder. And the radius is 4 feet. And the height is 10, the height is 10 feet. And it's filled with water up to 8. So this is 8 right there. And there is water everywhere up to here. Okay. And we have a pump that is going to pump the water. So the pump, so you have a pump right here from the top. So there's a pump here. And it's working on pumping the water out. Okay. And the question is, what's the work required to pump the water out of the tank? Okay, so how much work we need? We know that the work is force times the distance, but the issue here, what is the force in this problem? And as I mentioned when we're doing this section, is that the work to pump the water, which is on the top of the tank, is very different from the one at the bottom of the tank, because they have to be lifted by very, very different distances. Okay? And the idea was to divide the water within the tank into layers, so that the water within one layer, all the water within a layer will be lifted by the same amount. That was the logic. So anybody remember how did we do those problems? Anybody remember? Oh, that's a silence. All right, I'll remind you a little bit how we do that. So we created a axis, so we're gonna call that, for example, y-axis, x-axis. I don't really care what you call it, y-axis. And the way we've done it is the following. We took the water in the cylinder and we divided it into pieces. We divide into layers, horizontally. Horizontally. We take the water and we divide it into horizontal layers. So in the picture, something like that. That's what we did, is that. So we have water up to here. We divide, we took a layer here, top it with another layer. That's what we do. Top it with a third layer. And then we lift each layer by itself. Okay, that's really what we did. So we have one layer at the bottom, and then we have a layer here in the middle. And then we have a layer here. and so on and so forth. So we filled it with layer. And what we did is we picked up every layer by itself. We lifted this one by itself. And we ask ourselves, what's the work needed to lift that? The benefit of doing this is that if the height of this is very small, all the water inside this layer will be shifted by the same distance because the height is very small. So what we did is we divide into layer and then we lifted this and we ask ourselves how much work we needed. Then we took the one below it and we ask ourselves how much work we need. The one below it, how much work we need. So we lift each one by itself and we find the work to lift everyone by itself. And then we added the work. And the benefit, as I said, is to make all the water within a layer lifted by the same distance. So we have a control over the distance itself. Right, so let's do that now. So the idea is we're going to divide water into layers. In tank, into layers of height. Each layer should be very, very, very thin of height delta y. Okay, so this is my typical layer. We don't draw it at the bottom, or you don't draw it at the top. You draw it somewhere here. So this is my typical layer. Means I'm gonna split it here. So the typical layer is the cylinder. That's my typical layer. Okay. And the question, and this is my yi. From here to here. All right. And the question is, what's the force work needed to lift the layer? So the work is to lift a layer, one layer, is the force to lift it, which is the weight, because how much you need to lift a calculator is the weight of the calculator. So you think of a layer is just nothing more like this calculator, but cylindrical, and the weight to lift the work to lift it is its weight times by how much we're going to lift it. So it's weight of layer times the distance by which it's lifted. Times the distance. Okay. Now we do each piece by itself. What's the distance by which a layer is lifted? The distance by which a layer is lifted.
Would it be 10 minus yi?
It will be 10 minus yi. That's the distance. So I do every piece by itself. Now what's the weight? Now, since I gave you here the density is pound, it means this is a unit of weight, not of mass. If this is in kilogram, that will be the unit of mass. Okay, what's the weight? The weight is, this is filled of water. And the water weighs 62.4 pounds per feet cube. So every feet cube of water is 62.4. So to find the weight, we have to find the volume. It means how many feet cube is this little disk. We multiply by 62.4, which will give you the weight. So the weight is the volume of the layer times the density, which is 62.4. Okay, and this is feet cube, and this is pound per feet cube. So the unit is actually going to be pound, which is the unit of force. All right. So that's, if you guys are doing physics, most of you are doing physics by now, that's you analyze the unit to make things make sense. Now, finally, we're done. What's the volume of the layer? Back to you. What's the volume of a layer?
Is it going to be like 16 pi y?
Right, because each layer is this little disk here. That's the layer. The radius, regardless what the layer is in this rather simple problem, the radius is going to be a 4, right? That's the radius from here to here. Okay, it's the same radius because it's a cylinder. So the volume of the layer is going to be pi times, as your classmate said, the radius square times is a volume times the height, the little height of the layer, this little delta y we have, times 62.4. Okay, so or I can rewrite it as 62.4, I'm rewriting now, times 16 pi delta y. That's just the way. So the work now, so the work done on one layer, so work on a layer, I'm still working with one layer, is going to be the distance, which is 10 minus yi, times that, times delta y. And the total work is the sum of the work done on each layer. Okay. So the work is integral of all those little elements of work. So it's 10 minus y, and then we fix everything because this is not the way. 16 pi dy, that's the integral. And then always, 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 we have to see our limit. So we go back to the picture. What is our limit? To find the limit, we say, okay, what should we divide into pieces? Because to be able to cover all the water inside the tank. So from here, to cover all the water, my y should go from 0 up to here because there is no water here. So there are no layers in here. And this was 8. So it's going to be the integral from 0 to 8. And the rest, the rest is simple. Those constant go out. So you first take those constant out. You don't keep dragging them. And then we will have this integral. Okay. So this is just to remind you a little bit work, and your MATLAB homework for tomorrow is work. So I can remind you that. So that's a simple scenario. The other scenario that we have is something where we change the shape of the layer. I mean, sometimes the layer could be a cylinder, or the layer could be, I don't know, it could be something like a cube. That's a problem we did. Something like that. So sometimes the shape of the layer will change, but the principle is actually not changing at all. All right. Okay, tomorrow I'll keep on the review. It will help me if you guys tell me exactly what you like me to review. That will give me a lot of help. Otherwise, I will do whatever I think you guys need. Okay, but your input will be definitely appreciated. All right.